How can we compare the mass of two atoms since they're so very small? One way is to compare the mass of large numbers of atoms when both numbers are the same. But what container always holds the same number of atoms? Gas volumes seem to be a likely candidate for our container. We believe that equal gas volumes, under the same conditions of temperature and pressure, contain equal numbers of gas particles. So, we can compare the mass of two individual gas particles. The question is, are these particles atoms? We'd like to believe that sometimes they are single atoms. That way, gas volumes would be universal atom containers that we could use for comparing the mass of atoms. But what evidence do we have that gas particles are single atoms? Let's consider carefully the results of an actual gas reaction. Combine 2 volumes of hydrogen with 1 volume of oxygen under the same conditions of temperature and pressure. The product is 2 volumes of water vapor. Let's suppose that the hydrogen particles and the oxygen particles are single atoms. How many ways could these single atom particles combine together to create 2 volumes of water vapor? Let's examine the problem like this. Imagine you're a detective investigating a catering company. You can't get inside, though, but you can watch the trucking company which supplies it. First, they ship in 2 truckloads, each containing the same number of buns. Then 1 truckload containing the same number of patties. For every 2 truckloads shipped out with the same number of burgers. What's going on inside? First, the suspicious meat theory. The cook has 2 buns and 1 patty to work with. He matches 1 bun with 1 patty to fill 1 truckload with Yum Burgers. But he has a truckload of buns left over. Where does the second truckload of patties come from? From somewhere under the counter? Somehow he mixes up an extra truckload of patties to match with the second truckload of buns and make the second truckload of burgers. Now, let's compare buns and patties to atoms. 1 hydrogen atom combines with 1 oxygen atom to form 1 particle, which fills 1 volume. But there's a hydrogen atom left over. It combines with an oxygen atom, which is somehow created during the reaction. And the resulting particle fills the second volume. But matter can neither be created nor destroyed. Without the law of conservation of matter, chemistry would be a little more than magic. Can we afford to sacrifice this all-important law to justify a container for atoms? Let's try another theory. The bigger burger theory. The cook combines each patty with 2 buns, 1 on the bottom and 1 on the top. So he has 1 burger for every patty. These are bigger burgers and they fill 2 truckloads. Compare this to particles and volumes. 2 hydrogen particles combine with 1 oxygen particle to form 1 particle of water vapor. The particle is so large, it fills 2 volumes. A bigger product may be fine for hamburgers, but not for gases. Even though there are 3 atoms in it, the product is only a single particle. The rule is single particle, single volume, not two volumes. So this theory destroys our universal particle container idea that equal volumes contain equal numbers. So let's look at another theory, the crooked cook theory. The cook takes each patty and chops it in two. One truckload of patties becomes 2 truckloads of half patties. He combines each truckload of buns with each truckload of half patties and makes 2 truckloads of burgers. Now, let's look at particles and volumes the same way. Each oxygen atom splits. A hydrogen atom combines with each to form a particle of water vapor. But we defined atoms as the smallest indivisible particles of matter. If we can split them, they're not atoms. This theory, like the others, is just not good enough. What conclusion can we draw? The Italian scientist Avogadro was the first to propose a way out of our problem. It was Avogadro's hypothesis that equal volumes of gas at the same temperature and pressure contain equal numbers of particles. But in order to make his hypothesis match volumes he observed in the actual gas reactions, he also proposed that each particle of gas could contain no fewer than 2 atoms. He called these particles molecules. No one has yet proved Avogadro's hypothesis. But using it and his idea of molecules, it's possible to explain all gas reactions by matching every volume we observe in the laboratory with a molecule of at least 2 atoms. Two hydrogen atoms and 1 oxygen atom combine to form 1 molecule filling 1 volume. This leaves 2 hydrogen atoms and 1 oxygen atom, which also combine to fill 1 volume. Single particles, single volumes. The reaction balances with no need for magical appearances, swollen volumes, or split atoms. But there's been a price. We set out to find a universal container for atoms, and we had to give it up. Instead, we have found a universal container for gas molecules. Under the same conditions of temperature and pressure, a gas volume will contain the same number of any kind of gas molecule. This allows us to compare the mass of gas volumes and so compare the mass of single molecules. That is relative molecular mass. Now, is there a way of taking relative molecular mass and finding relative atomic mass?